Welcome to this explainer. Think of me as your personal lab engineer today. We're going to progressively unpack the fundamental architecture of Docker. Now, if you've ever felt completely overwhelmed by terms like images, containers, volumes, and ports, don't sweat it. We're going to build your mental model from the absolute ground up, completely logically and without all that confusing jargon. By the time we're done here, you're going to know exactly how this technology works.
So let's start with a scenario literally every developer knows all too well. You've just spent weeks building an application. You're using Node.js for the backend, Postgres for the database, and every single test passes perfectly on your laptop. You proudly send the code over to a coworker. They clone it, install it, run it, and it immediately crashes. No way, right? They look at you look at them, and eventually you have to utter the most infamous sentence in all of software engineering. Well, it works on my machine. It's frustrating, it's honestly a bit embarrassing, and it wastes hours of debugging time.
Okay, let's dive into this, because here is the real truth of the matter. This is an environment problem, not a code problem. You see, an application doesn't just run in a vacuum. It heavily depends on a very specific runtime, like the exact version of Node you happen to have installed on your specific laptop, as well as OS libraries, configurations, and precise network setups. If your coworker's laptop has even a slightly different setup, the whole app breaks. So the fundamental question becomes, how do we package an application so that its exact required environment travels with it perfectly every single time? Well, that is the core problem Docker solves.
Now, when people first hear about packaging an entire environment, they usually jump straight to virtual machines. But we need to build a stark boundary right here. A container is absolutely not just a tiny virtual machine. A virtual machine virtualizes the physical hardware itself and runs a full, heavy guest operating system. It's bulky, and it takes minutes to boot up. Containers, on the other hand, isolate application processes by fencing off a small section of the computer while still sharing the underlying host OS kernel. Because they aren't loading up a whole new operating system from scratch, they are remarkably lighter, highly efficient, and boot in literally seconds instead of minutes.
To truly understand Docker, you've got to master the core dichotomy between an image and a container. Let's start with the image. A Docker image is a packaged, read-only template. It contains the exact instructions, all the application files, and every single environment dependency needed to run your app perfectly. Think of it as the ultimate, unchangeable blueprint, or a completely frozen snapshot of your app at a specific point in time. Because it's read-only, it can never be altered once it's created, which is what guarantees perfect consistency wherever it ends up going.
A Docker container, on the flip side, is a runnable, isolated instance of that exact image. Once you tell Docker to run an image, it spins up a container. And because the image itself is just a read-only blueprint, a single image can spawn tens, hundreds, or even thousands of identical containers right across your infrastructure in seconds. The container is the active, breathing process born from that blueprint. It's the actual living application that your users are interacting with.
So the absolutely crucial point we need to cement into your mind is this back-to-back relationship. You build the image, you run the container. The image is the packaged template. The container is the running instance. If you can keep this distinction crystal clear, everything else in the Docker ecosystem becomes significantly easier to understand and troubleshoot. It really comes down to you build once, you run anywhere.
So how do we actually construct this magical image? We write what's called a Docker file. It's essentially a highly structured recipe, just a simple text file read from top to bottom by Docker to build your image layer by layer. You start with from to set your base environment, like pulling a basic node setup. Workdir sets up the internal folder. Copy moves your source code in, run executes commands like installing dependencies, and expose documents which network port the app uses to communicate. It's really simple, step-by-step logic.
Now, here is a massive optimization trick that totally separates the beginners from the pros. Docker caches each layer it builds. When you're structuring that recipe, ordering matters immensely. If you install your heavy dependencies first, like your package.json file, and then copy your frequently changing source code, you save yourself massive headaches. This way, if you just change one single line of application code, Docker simply uses the cached dependencies and doesn't have to painstakingly reinstall the whole shebang from scratch. It saves you huge amounts of time during development.
All right, so we have our image built and optimized. What exactly happens behind the scenes when you open your terminal and actually type Docker run? Well, first, the Docker engine retrieves the image. Second, it creates the isolated container structure. Third, it adds a thin, temporary writable layer on top of that read-only image so the app can actually function. Fourth, it configures the internal networking. And finally, it starts your application process.
All of that happens in a matter of milliseconds. Compare that to the minutes it takes to boot a traditional virtual machine, and you really begin to see why Docker completely revolutionized the industry. But wait a second. Our application is now completely trapped inside an isolated container. How do we actually reach it from our web browser? For that, we use port mapping. Think of it kind of like a hotel switchboard. If you map 8080 to 3000, the port on the left, 8080, is the port on your host machine, the one you'd actually type into your browser. The right side, 3000, is the isolated internal port the container is listening on. Port mapping simply tells Docker to act as a bridge, instantly forwarding external traffic from port 8080 directly into the isolated container's internal application. That covers us reaching the container from the outside, but what about containers talking to each other? Let's say your new API needs to talk to a PostgreSQL database container. A classic beginner mistake is trying to connect the API to localhost. But here is the catch. Inside the API container, localhost only refers to the API itself. It's literally like trying to call your friend but accidentally dialing your own phone number. Docker networking controls communication via container names instead. So your API would genuinely connect to an address like Postgres 5432. It is a completely self-contained, highly intelligent network. Now, this strict isolation is absolutely brilliant for security and packaging, but it introduces a rather terrifying persistence problem. What happens to our database state if we need to update or delete the container? If Postgres writes all of its user data, passwords, and transaction orders directly into the container's temporary writable layer, and we replace that container, well, the data's gone forever. I'm talking a total irrecoverable production wipeout. Containers are meant to be temporary and replaceable. Writing critical data inside them is a complete recipe for disaster.
The solution to this is decoupling. We separate the temporary container lifecycle from the persistent volume lifecycle. You can think of a Docker volume like a rugged external hard drive plugged directly into your container. A Docker volume exists safely outside the container's isolated file system, sitting in a dedicated protected location on your host machine. Because of this physical separation, you can safely destroy the database container, spin up a brand new upgraded one, plug that exact same volume back in, and all your data remains perfectly intact.
Okay, so we know how to build, run, and protect our data locally. But how does this smoothly transition to an actual deployment server? Let's trace the image distribution pipeline. You build the image and tag it with a version number. Then you push it to a registry, like Docker Hub, which is basically the GitHub of Docker images. Your production server then simply pulls that exact same identical image from the registry and runs the container. The built image becomes the consistent, deployable artifact. It's the exact same binary bits running in production as they did right there on your laptop. Now imagine manually managing a real modern application stack with all this knowledge. Starting the private network, starting the database, carefully mounting the volumes, setting up secure environment variables, starting the Redis cache, starting the API, and mapping all the correct ports. Typing out these exact terminal commands manually every single day is tedious, it's incredibly frustrating, and it is a guaranteed way to make a typo and break production on a Friday afternoon.
And this exact nightmare scenario is why Docker Compose was invented. While a Docker file asks, how do I build this single image, a Compose file zooms out and asks, how do all these services run together? A Compose file is a declarative map of your entire application stack. Instead of running a dozen fragile terminal commands, you write one clean file. With a single command, you launch your database, your cache, your API, the network, and the volumes, all perfectly orchestrated and connected together seamlessly.
We've covered a tremendous amount of ground here, so let's slow down just a beat and progressively reconstruct the mental model we've just built together. You write your code. You use a Dockerfile recipe to define the environment. That builds a frozen, unchangeable image. You push that image up to a registry. Your deployment server's Docker engine pulls it and finally spins it up as a running, interactive container. That is the complete Docker lifecycle. If you can grasp this continuous flow, you understand 90% of what makes Docker so incredibly powerful. However, before we wrap up, we do need a quick reality check. Docker is amazing, for sure, but it is not magic. It does not automatically grant your application infinite scalability, perfect high availability, or bulletproof security. And it certainly doesn't fix a poorly designed application architecture. Remember, if a physical server's motherboard catches fire, every single container on that server still crashes right along with it. Docker beautifully packages individual workloads and makes them portable, but it doesn't run the entire data center for you. Which brings us to our final thought, and really the next massive challenge in modern software engineering. What actually happens when these containers need to scale out across dozens or even thousands of physical machines? How do you ensure zero downtime if a whole data center loses power? How do containers self-heal? Well, that requires an entirely different beast of orchestration. But hey, that is an explainer for another day. Thanks for joining me in the lab. Keep building, and I'll catch you next time.